Hello. So from last video, we learned one-dimensional kinematics. This time, I'm going to be telling you how we derive these one-dimensional kinematics and how to better actually utilize them. So this video could give you a better understanding of how these kinematic equations and formulas work and how you could better utilize them more flexibly. So first, before we start, I'm going to define to you what is free-flying objects, or in this case, projectiles. So a free-flying object is any object that accelerates only, remember the keyword is only due to gravity, influence of gravity. And free-flying objects will usually ignore wind resistance, at least in a high school level. So this really makes your life easier because no matter how large an object really is or how heavy it is, it's always going to have the same acceleration. So say we threw a rock and a feather, pardon me for the drawing skills, down to say the Eiffel Tower, and then they will land at the same time if there's no wind resistance, or their magnitude of acceleration will be the same because there's no wind resistance. And this is why it's so beautiful that it's so much easier for us, at least in high school. Later on, some questions might actually ask you to calculate wind resistance, but in high school, generally, you won't see anything with wind resistance. Now, let's talk about how the first kinetic equation has been derived, a formula. So first, the first kinetic formula is final velocity is equal to initial velocity plus acceleration times time. So this is probably one of the easiest ones to be derived because we can just rearrange it. So accelerate, because we can rearrange it from this. Acceleration is equal to change in velocity over changing time. And this is actually the equation for average velocity here. Sorry, acceleration here. Now then we would simply rearrange this. What it would look like on the top is it would look like velocity, final velocity minus initial velocity, and then over the change in time, over delta t. And then we would simply rearrange it. We would move final velocity to the left side, equal to initial velocity plus acceleration times changing time. And then if we simply agree to say that, well, in this case, time is going to be changing time, which is usually how it works. You would start at 0, then you will go to your sort of your time in the end. So it would just be changing time. So we could actually simplify this to velocity is equal to initial velocity plus acceleration times time. So this is fairly simple. It's just simple algebra where you rearrange these numbers and I guess variables. So you can find the first kinetic formula. Now we're going to the second kinetic formula, which is honestly one of the more complex ones. So it looked like delta x is equal to velocity plus initial velocity. Sorry, initial velocity plus final velocity plus initial velocity. There we go. Over 2 times time. So here on the right side, you can see that I actually have included a graph, which is actually the best looking one, and then a very interesting way to actually represent this visually. So the area under any velocity graph is displacement, and then we can see that by looking at the axes. So we have velocity right here in the term meter per second, then we have time, which is in the unit of second, then we have t, and then initial velocity and final velocity. So in this case, we will say that changing x or delta x is going to be the total area of this triangle. And then we can continue. Then we can actually break this graph up into 2 sections, or this area into 2 sections: a red rectangle and a blue triangle. So the height of the blue triangle is, the height of the red rectangle is velocity 0 or initial velocity. So this is height. Height is v0. And then the width of or the length in this case of the rectangle is t. So the area of the rectangle rectangle is initial velocity times times. Then we have the base of the triangle, which is again t, and then we have the height being v, final velocity minus initial velocity, which will give you this length right here. So the triangle, the area of the triangle would be half of time times final velocity minus initial velocity. And then if you add these all together, you would actually, so you have the total area, which is delta x is equal to plus half of t times initial velocity. There we go. And then we distribute the factor of 1 over 2t, we would get delta x is equal to 1 over 2 velocity, final velocity times t plus 1 over 2 initial velocity times t. And then we simplify, we will get delta x is equal to the velocity plus final velocity plus initial velocity over 2 times t. So it's quite beautiful that you can see this visually. And then for me, it really helps to see this visually. And then this formula is also interesting because if you divide both sides by t, it actually shows that the average velocity and the average velocity. So if you divide both sides by t, you will get sort of what I wrote here. And then this shows the average velocity equals to the average of the final and initial velocity. So this is the average. Right here is the average velocity, and then here is the average of the final and initial velocity. So this is very interesting. An interesting thing. Is it useful? In some cases it is, but in most you won't really need to remember this. And then this is also only true assuming that the acceleration is constant, since we derived the formula from a velocity graph, which is what this is right here on the right, the graph, with constant slope and acceleration. So the slope is constant. There's no something which look like this. So let's just assume that it's a constant slope. Perfect. So this is the second kinetic formula. For the third kinetic formula, we will actually also use the same graph because it's a velocity graph. So it's actually quite helpful here. So the third kinetic formula look like this: delta x is equal to initial velocity times time plus half of acceleration times time squared. There are a couple of ways to really derive this formula, but then as I like to see things visually, we are going to do the geometric derivation first. So since the area under velocity graph gives a displacement of delta x, so we know that as from the previous graph, previous question or derivation, that delta x is equal to the total area again. And from the previous question, we would know that the rectangle is velocity times rectangle is v0 times, or initial velocity times, and then we also know that on the second graph it's going to look like half of acceleration times time squared, which is what the triangle is. So this is basically it. It's rather simple for this question because from the previous question we already know what a lot of these are. So this is triangle and this is rectangle. From these, then we would put them together, and then delta x, which is the total area, then you would take t plus half of acceleration times time squared. So now we know what the total area is right here. Now we've done the geometric way, which is my favorite way of doing this. Then we are going to get started on plugging and chugging in derivations. So that can actually be found by plugging the first kinetic formula into the second kinematic formula. In the second kinematic formula, we have this. It's equal to velocity plus final velocity plus initial velocity over 2. And then we also know that velocity is equal to initial velocity plus acceleration times time. So then we can actually plug that right into this velocity. So what this would look like is time plus velocity over 2. So this is what we would look like, and then we can combine some terms here. So first we will have 2, so then this would be 2, and then that will cancel out. So then we would have delta x over t, which is going to look like initial velocity plus acceleration times time over 2. And then here we multiply both sides by t to make sure that the right side, or sorry, the left side always stays as delta x. And then let's just look like delta x is equal to t plus half acceleration times time. Great. So these are the 2 ways you could do this, geometric or by just doing the math. I personally like visuals, so I would personally go with the first one, but it doesn't matter. It's always good to know both ways because you might actually want to use them, or in a test, the teacher might ask you to prove it or to say how you derive from it. So it's always good to have both. Now, fourth kinematic formula. So to derive the fourth, we actually have to go back again to the second. So we have delta x is equal to final velocity plus initial velocity over 2 times time. So now we want to eliminate time from this formula, really. And then to do this, we have to solve the first kinematic formula for time. So if we plug the equation in, which we know is the law of initial final velocity is equal to initial velocity plus acceleration times time. We will plug the t in, so we know that delta x is equal to final velocity plus initial velocity over 2 times final velocity minus initial velocity times, sorry, over a, and then now we multiply the fractions to the right hand side, and then we would get delta x is equal to final velocity squared minus initial velocity squared over 2a, and then we solve for velocity squared, so we just simply rearrange the formula, and then we would get this 2a delta x. And here you go, this is the fourth kinematic formula. Unfortunately, there isn't really a definite graph. There's no graph to show this, so this is really the best way you can do this. And then it's actually quite interesting to see that the third or the second, or the third and the fourth could actually be all derived from the first and the second, and then which is always fun, I guess, in some sense. So let's get started on the next one. Now, there's actually a fifth kinematic formula, which is, I guess, in a sense, it's a hidden formula. It doesn't really make sense too much. But sorry, it's not that it makes sense. It's that it's really just the third formula. Because if we looked at the previous ones, the first one is used for when you're missing delta x. The second is used for when you're missing acceleration. The third is when you're missing initial velocity. The fourth is when you're missing time. But it's interesting to see that you don't have one which is accommodated for missing the initial velocity. So this is where I guess sort of the fifth one comes in, which is delta x is equal to velocity times time minus half of time. Right. And then this looks exactly like the third, actually. So not exactly, but this looked like the third. But then we need to remember the third. So this is the third one is delta x is equal to velocity, initial velocity time, plus half of acceleration times time. So it's just the fifth is just the third, except right here, that's a minus. So this is just a minus. And then it's often isn't as useful as the initial velocity because most questions would give you the final velocity, but it's always good to know this one. Now, why is this so complex, or what's so confusing about kinematics formula? So people oftentimes forget that kinematics formula are true assuming that acceleration is constant. So you must always remember acceleration is constant for this question, for the acceleration. So when acceleration is not constant, then these formulas do not work. And then these are usually used in time intervals considered. To say this is one, and then you would have another one, and you have another one, and you use another one. So you must look at these separately. You must look at these each section separately as their own, instead of trying to say look at the whole as their own. Because if you, so here's the initial velocity, sorry, here's the initial velocity, here's the final velocity for this section. You can't look at here and then here. That doesn't make sense. So you have to break it up, and then this is where people often get it confused, because if you don't break these up, then it's not going to make sense. Your answer is, of course, going to be incorrect. And then sometimes a known variable will not be stated in the question. Rather, it's going to sort of like a code word or like a different wording of it. So they won't say the initial velocity is this, the final velocity is this. They won't tell you that. What they would maybe say is started from rest, which actually just means initial velocity is equal to 0, because it started from rest, dropped, which usually just means we'll find is 0 because it's dropped from the tower, so its initial velocity is 0, comes to a stop. That means that the final velocity is 0. And then it's also important to remember that the magnitude of acceleration is always, no matter for what object, is 9.81 meters per second squared. And then if the question does not say, but it's always, if it's implied there's a free-flying object, then you would just simply use it. And then you must also remember that all kinematic formulas, all variables from kinematic formulas are, say, delta x, velocity va, except for t can be negative. So these can all be positive or negative, whereas t have to always be positive. So many people forget this. And then the missing negative sign is a huge common, a huge error that people usually make. And it's a very common source of error. And then if upward is assumed positive, then acceleration due to gravity must be negative. So you must always get your reference correct. If your reference is upwards, then whatever's dropping down is of course going to be negative. You might laugh at this, say, well, that's pretty obvious. When you're actually doing a question, you would be surprised at how many people actually make mistakes like this. Now, the third kinematic formula might require the use of the quadratic formulas, and then that sort of get things more complicated. And then people forget that even though you can choose any time interval during the constant acceleration, as I said earlier on, the kinematic variable you plugged in must be consistent. And I'm saying this again to reinforce this, because if it's not constant, then it doesn't make sense. They have to be at these 2 points. It must be constant and consistent, to the time interval. And in other words, initial velocity has to be the velocity of the object at the initial position at the start of that time interval, say t. And then the final velocity has to be the final velocity and final position. And then if it changes, then it starts again. So here's the new initial velocity, here's the final velocity, then we change. So you must remember that you must treat these like separately. So what you could do is, what I like to do is, you would say take the question as a whole. You would first draw this out or graph it out. Then you would divide up these sections and then ignore the rest for now. Just look at this section. Once you're done, write it down. Just look at this section. That always helped me. And then that's a small trick I would like to tell you. So this is the second of the third video. For the final video, I'll be doing some questions and along with some answers with you guys. Stay tuned and have a lovely day.